Hello everyone, welcome back. Yes, today I'm quite excited because I've got quite an abstract, nonsensical video for you, and I was, well, I was glad from a content creator perspective to see that there were no YouTube videos on the subject that I could find. Even though it's the type of thing that, I feel like it's just kind of funny, it's a good YouTube video to make. In my opinion, at least. Hopefully you agree since you clicked on the video, but thank you for coming here. Anyway, yes, today I'm going to be talking about -1 categories and -2 categories. And the motivation for this comes when we look at the periodic table of categories. And yeah, this goes on further. This isn't the whole periodic table or whatever, but I'm just giving you this excerpt to give you an idea of what's going on here. I'll link the paper that I got this from. I can't remember the author's name off the top of my head, but it's a great paper. When I have spare moments, I like to, at the moment I'm flicking through it, and yeah, I'll link it down below. Anyway, let's get into the video. So the periodic table of categories is as follows. So here's how we define it. So let's look at this column, for example, n equals 0, the n equals 0 column, all right? Now, what does this mean? The way we define it is, in this position, right here, n equals 0, k equals 0, we have a 0 plus 0 category. So we have a 0 category. And the morphisms, well, okay, in a 0 category there are no morphisms, so there's no idea of that. So we just have a 0 category, which we can, as long as we're in a small category, we have no set theoretical issues, just sets. Now, here we have 0 plus 1, so we have 1 category, which is a category, and k equals 1 corresponds to the fact that any j morphisms where j is less than k, there's only one of them. So for what numbers are less than k equals 1? Well, just 0. So there's only one zeromorphism, but a zeromorphism in, normal language is just an object. So we have a 0 plus 1 category with 1 zeromorphism. So a category with 1 object, and if you watch not my previous video, but one of my previous videos, I talked about how a groupoid with 1 object is a group. Well, in a very similar way, a category with 1 object is a monoid. So in this column, in this slot here, we get a monoid. And then 0 plus 2, now we have a 2 category. So what's a 2 category? Well, okay, we're taking everything as weak as possible. So here I mean a bicategory, but anyway, okay. I don't want to get into technical details because that's not the point of this video. We're just thinking of a 2 category as something which has objects, has morphisms, 1 morphisms between the objects, and then it has 2 morphisms between the 1 morphisms. So for example, the 2 category of categories, you'd have objects being categories, 1 morphisms being functors between the categories, and then 2 morphisms being natural transformations between the functors. So that's how when you think of 2 categories. Of course, there's more technical details that need to be sorted out there, but that's roughly what they are. And k equals 2, so we need all the j morphisms for j less than k, there to only be one of them. So for j less than 2, that means j is 1 and j is 0. So we have one morphism and we have 1 zeromorphism. So what does this look like? We have 1 object, star, aka the 1 zeromorphism. We have 1 object, we have 1 morphism from the object to itself, and then we have as many 2 morphisms as we like between the identity and itself. So in this way, we still get a monoid for very much the same reasoning as a normal category of 1 object gives us a monoid, because the 2 morphisms between this just give us our elements. But in this case, because of the technical way that a 2 category is defined, we need to have good properties when we're going between 1 morphisms and 2 morphisms and so on. We actually get a commutative monoid, and that could be the subject of another video. where I, introduce two categories more formally and then show that the two categories, one object and one morphism is a commutative monoid. But basically a commutative monoid. And if you keep going down from here on out, from k equals 3 onwards, down this row n equals 0, you just get commutative monoid again and again. Okay, good. So it stabilizes. Then for n equals 1, this row, okay, n equals 1, k equals 0, so we get a 1 category. And we have as many morphisms as we like because k is 0. So we just get a regular old category. Then n equals 1, k equals 1. Here we have 1 plus 1 is 2, so we get 2 category. And k is 1, so the j morphisms for j less than 1, there's only one of them. AKA, we have a 2 category with 1 object. And that can be identified with monoidal categories. Again, not something that is the subject of this video, but that is something that's true. And then these two, I can't lie, I just copied it from the table. I have no idea, like, any intuition for what these two mean, but for completeness, if you want to let me know in the comments what's going on here, feel free to. But in the column n equals 1, k equals 2, so we're in a 3 category with the same thing as before. We get braided monoidal categories apparently. And then n equals 1, k equals 3, we get symmetric monoidal categories. And if you kept going down, you would just, again, it stabilizes, so you keep getting symmetric monoidal category, blah, blah, blah. And then you could keep going this way and down and whatever. And you'll get that it stabilizes here, it stabilizes here, it stabilizes here. Cool. So these guys who were first looking at this this periodic table, so to speak, they were looking at it and they showed some theoretical physicist, Imperial. And the theoretical physicist said, okay, cool, but you're not starting at the right place. Like, why would you start here? So you know how we have 3 different things in this row, then we have 4 different things in this row, 5. Why would you start at 3? Like, that makes no sense. You should start at 1. There should be 2 more columns that you're missing. And then the category theorists were like, okay, mate, like, I know we do abstract nonsense here, but like, have some respect. Like, we're not. What is a -1 category? Like, don't be ridiculous. Oh, get out. You know what I mean? That type of thing. Anyway, turns out they were that ridiculous. They are that abstract. They are that nonsensical. That it sort of bugged them. And then they thought, okay, that guy was right. We can actually have -1 categories and -2 categories. And that is my goal today, is to explain what those are. And to explain why they are what they are. So okay, good. So we know that an n category has objects. It's got 1 morphisms between the objects. It's got 2 morphisms between the 1 morphisms. Blah, blah, blah. It's got j morphisms between the j minus 1 morphisms, all the way up until n. So what we want to think of is an n category is just an infinity category, except once you go above n, so the n plus 1 morphisms, those are all just the identity. So it's all trivial, but technically we're in an infinity category, just that as soon as you go above n, all the morphisms are identities. So in this way, with this in mind, we can now motivate -2 and -1 categories. So, okay, let's proceed. What color pen is this? Oh, blue. Yes, okay, blue. Okay, so let's proceed. So, if we look at an n category, and we look at 2 j morphisms, right? So these j morphisms will go from some j minus 1 morphism z to another j minus 1 morphism z prime, and we say that they're parallel if they go between the same 2 j morphisms, like so. And in this case, we can define a vertical map between the 2 j morphisms, because it makes sense to do such a thing since they're going from the same starting and ending point. And so we can construct the set Hom xy. Now, what exactly is this? So we're starting out with j morphisms. So the objects of this, sorry, I shouldn't have said set. We can construct a category. But what exactly is it? Well, the objects are j morphisms now. The morphisms are j plus 1 morphisms. The 2 morphisms will be j plus 2 morphisms, and so on and so on and so on until we get to n morphisms. And so because we're starting now not at 0 but at j, we've offset our definition so that instead we have an n minus j minus 1 category. For example, if we took j to be 0, then this would just be objects. So we would have, now that the objects are 1 morphisms, because yeah, if x and y were objects, say x and y are j morphisms, if j was 0, x and y would be objects. So hom xy, this category, the objects would now be morphisms, 1 morphisms. The 1 morphisms would now be 2 morphisms, and so on and so on. So the n morphisms would now be n minus 1 morphisms. So we'd get an n minus 1 category. And similarly, if you pick j to be anything other than 0, you get an n minus j minus 1 category. Okay, cool. So now they just said, okay, let's pick j equals n. And at first, you would think that doesn't make sense because we're in an n category. So how could you have n plus 1 morphisms between your n morphisms? Because that's what you would need. But with this intuition in mind that really we're working in an infinity category, really we're working in an infinity category, just that all the n plus 1 morphisms and above are trivial, we can sort of do this. We can. It's just maybe not that interesting. So let's pick j to be n. So we have hom of xy, right? Where these are n morphisms. Now n plus 1 morphisms are they are identity maps, right? So this is equal to either the empty set if x is not equal to y, because there's no identity morphism between x and y if they're not the same thing, or is just equal to the set with one element, we'll call it identity, if x is equal to y. And this is all we have. So this is a minus 1 category. And typically the convention is, instead of writing it like this, is a minus 1 category just consists of false, which corresponds to the empty set, and true. So a minus 1 category is really just truth values. Okay, that's kind of weird, but cool. So now let's do the same thing for n equals minus 2. So what's a minus 2 category? Well, a minus 2 category, now we have morphisms. We need to look at hom of xy, where x and y are n plus 1 morphisms. But n plus 1 morphisms can only be the identity, so we have to have hom of x. They have to be the same thing, because we only make sense of this when the two morphisms are parallel. So they necessarily have to be both the identity. And of course, there's only one such morphism, which is again the identity. So a minus 2 category, we have even less options. A minus 2 category, because it always corresponds to just the identity between two n plus 1 morphisms, is just true. We just define it to be the truth value true. And that explains the thumbnail where I say get this man a minus 2 category, because of the meme where you say get this man a true, whatever. Okay, I was trying to be funny there, hopefully it amused you. But yes, that is why minus 2 category is true, minus 1 category is truth value. So that fills in these two things. And then we, for completeness, we can think of a monoidal minus 1 category, which is this spot here. Minus 1 plus 1 is just 0, so we're in a 0 category. And we have one zeromorphism, i.e. we have one object. So again, a monoidal category is just a singleton set, which again we define to just be true. So I could have also made the thumbnail, get this man a monoidal -1 category, which is almost funnier because it sounds more complicated, but okay, yes, good. Okay, and that's what I wanted to say in this video. So -2 categories and -1 categories are a thing. They're kind of trivial, but it's funny that they exist. Yes, that's all I wanted to say for now, but expect more abstract nonsense coming your way at some point soon, because I'm loving it at the moment. So yeah, hopefully more videos on a similar vein will come through. And I did check the camera angle before I filmed this time, so you should be able to see me. Yeah, so hopefully you enjoyed. Hopefully I've illuminated why a -2 category is just truth, and -1 categories are just truth values. So yes. Okay, well I hope you enjoyed, and if you did, then stick around for the next one. See ya.